Okay, so what Ms. Kenny just passed out to all of you is our bell ringer. So what we're going to do is we have a function at the very top. You guys can get one? We're not turning this in, but this is practice for you guys. So what this sheet is going to talk about a lot of stuff that you guys already have talked about and a few things that we haven't yet. So for now, what we're going to do is just going to grab this eraser really quick. So these are notes for you guys is what this is. This is a great sheet for you guys to write on for yourselves. That will help you review all of the topics that are on your proficiency scales all at once. What is the very first question that I ask you guys on this bell ringer? Those that have it. Graphing the function. Yeah, so we're going to start by graphing that function. So, let's slash them right in here.
So you're talking about the A and B here?
Yeah. So what we're going to do, so we're going to focus on just A and B for now. A, you're going to go ahead and graph this function, something we've talked about before. And after that, I want you guys to practice writing it in standard form as well. You'll all see that you have white books around that all have your group at the top left. So go ahead and go to those vertical surfaces and go ahead and graph. See if you can graph this function.
Just one thing to clarify is we're graphing this without calculators, using the factors. Mr. Hobby and I settled on this starting problem to help you prepare for your demonstrate understanding tomorrow. So this is to help you prepare for that.
So 4s, you're up here.
Kennedy, you can go back there. I'll print this out. Grab a calculator if you need it.
Okay.
You look more than chicks. What's up, boy? Sweet boy. They can see me clearly. They can see me clearly.
They couldn't see your face, but they see you though.
Okay, so go ahead and work on here. You don't like these?
They don't draw good. See, look.
Don't worry about that corner. Good marker. Good at it. Nice. Where are we? Amber. Nice. Alright. We should be graphing, using those linear factors. So I like that we're going to graph those zeros here. When I say graphing linear factors, did you get it? Yeah, okay. So what is it that we learned from graphing? What are those factors? So we have the line intercept, right, and then we have the slope there, right? Let's get it. Same thing.
Already.
So what we can do is we can go ahead and graph those individual vectors. Yeah. Go ahead. You can go ahead So do you remember when we were talking about like multiple lines, right? Do you remember the no? Okay. So
Can't go to sleep.
go ahead and start out by graphing.
Oh my God.
Graph the individual factors. What the y equals 2 points will look like. Do that on your vertical surface. Pull this off.
No.
You want to graph first? Yes. So how are we going to... Hey now.
First off, to hold on to those papers, but in general, there's been a lot of times, especially in the last few weeks, where you have been on task of talking to others, like people, whatever. Be careful, it's negative x minus 1, isn't it? Yeah. So it's going to bounce there. Think about other things you can do. Let me finish solving for 1. Let's could I mess
But it's function is defined by some factor.
Right, you didn't look at it.
Well, that's something you can do to find those zeros. But how are we going to know like when it's
if you're trying to do what I agree.
Why don't you ask Todd? Seems like Todd.
It's not working.
Feel free to ask other groups.
Preston, you have to do your work. Now,
We're talking
no, you trying to screw around. No, I'm not. Preston.
You want to solve for what?
We have to use questions to bring it about.
So negative 1 is right. I want to make sure we're using that full
I feel like I'm being effective. So we're in it. I'm trying to find a way to move forward so that we can have
He said we didn't have to put it. Oh.
Thank you, Amber. Thank you, Val. Thank you, Madison.
That's what Mario.
Thank you, Spencer. Thank you. Guys, raising your hand and turning back to your board makes no sense. When I'm raising my hand, there's a reason. Well, this man's doing something else right now. I'm trying to get everyone else's attention. Okay, so it seems like we're stalling a little bit. So let's come together. Let's talk about what we're doing here. So, the first question, when I asked to graph using the function's linear factors, what do I mean by that? The linear factors? What are the linear factors?
The lines.
The lines, but where are the lines happening?
On the x-intercept.
On the x-intercept? Oh, can't really see the x-intercept. So x-intercept, the line is different. Where are the lines happening? What's causing us to make those lines? Is it recording over there? Okay, thank you. So, when I look at this function, what are my linear factors? What do I mean by that? I agree that we're talking about lines here, but what are my lines? Okay, so you're saying this is a line,
This is a line, this is a line.
Yeah, so guys, notice up here, this function is being defined as the multiplication, as the product of 3 different factors. These factors, those are things that we multiply together to get a product. And are each of these linear?
Yeah.
Yes, they're linear. So these are these linear factors. What are we going to do with x minus 3? Can we graph that? Yeah. Do we know how to graph 2x plus 2?
Yes.
Yes. Do you know how to graph negative x minus 1? Yes, exactly. So what the 9s did up here, they drew each of those individual lines. That is what we want to do. Now I noticed people were finding, they were setting the equation equal to 0, using that zero product property. I love to see that, and I'm glad that we've gotten comfortable with that, especially when we're in factor form, especially when we have multiple factors. I love to see that. That is useful information, because yes, now we know that we have these zeros. That's a great thing to know. But we want to know more than just the zeros, more than just the x-intercepts. We also want to see what is the graph, what is its shape, what is it doing? And that, from what we talked about before, that's the usefulness of drawing those linear factors. Okay? So, I want us to practice one more time. So let's go ahead and go back to your vertical surfaces.
Can I
Yes.
point out
Okay.
2 quick things really quickly, just because I've seen multiple issues with this. One, really quickly, guys, y'all are working on a grid here, and we're marking lines that aren't necessarily on that grid. So
I marked it.
can you learn? Just learn, okay? So what I would point out is 2 things. One, I saw a couple who were in other places who were not actually marking on the grid lines. Use the grid lines. But 2, when I look right here, you see how 1 block is 1 unit here? But then how many blocks are they going here? 2. Are those the same? No. So make sure that you stay consistent with those, and then use that grid, right? That grid is there to help you make sure that whatever scale you use the whole time. The other thing I want to caution y'all is this right here. I need us to be careful with our work. This group, and it's just good to learn from this, they divided by 2x. But really quickly, what is 2x divided by 2x? Not negative 1. Positive, but it's a full 1. Notice it's not x. It's 2x divided by 2x is 1. Make sure we're paying attention to these things. And then I'm left with 2 divided by 2 is 1, so 1 divided by x. But that's not what I want. I want what x is equal to. What they did is mathematically legal. Completely fine. Totally okay. However, does that tell me what x is equal to? No. What should we have done here instead of divide by 2x? Just divide by 2. Slow down and pay attention to that. Because you can sometimes, like I think they got the right answer at the end, but this is where you would see like a P on your demonstrate understanding, because it's a procedural. Oh, it's supposed to be -2. Yeah, it is. Thank you for catching that as well. So, pay attention to the small details, but again, we're multiplying, so we divide by 2. So x is equal to -1. So pay attention to your zeros, pay attention to your slopes, pay attention to your y-intercept. Okay? So, where do you have them going?
Yeah, okay. So,
Do you want them to finish this problem? And we can give the others a separate one to practice with, the ones who are already done?
yeah.
So just go over.
Yeah.
Okay, so let's go over from here. How we're going to graph this. I'm going to steal this group up here.
100%.
So, I have my
Accuracy,
linear
but
factors.
we're
What am I
going
going to do with my linear factors?
Completing it genuinely.
Let's graph them. Yes. Starting with x minus 3. How am I going to graph that? Figure out the x-intercepts? You could do that. Yeah. The negative side.
Wait.
Graphing x minus 3. Love to hear from
-3 on the x-axis.
-3 on the x-axis. Will the point
That's the
y equals x minus 3?
Oh, -3 on the y-axis.
-3.
On the, you said on the y-intercept?
I mean y-axis.
On the y-axis.
Yeah.
Okay. So starting with -3 on the y-axis, why is that? That's the y-intercept, yes. When we're in mx plus b, b tells us our y-intercept, okay? And then what am I going to do from there? Once I identify my y-intercept? We need our slope. What's our slope? Our slope. Yeah, so we have nothing, so it doesn't look like there's anything in front of it, but that's understood to be a 1 times x. So our slope is 1. So I'm gonna go up 1 over 1, up 1 over 1, keep going. That's one line. Okay, I'm gonna do the same thing for 2x plus 2. What's my y-intercept? 2. What is my slope? 2. There we go. Y-intercept of 2, slope of 2. Up 2 over 1, up 2 over 1. Write that down.
That's a little wonky.
Yeah, that was a little wonky, I agree. Here we go. Okay. Negative x minus 1. How am I going to graph that one? Negative 1 is my y-intercept. That's my slope. Negative 1 over 1. Negative 1 over 1. Okay. So, what am I going to do here to construct my polynomial?
Plus minus with the what you call it? You gotta make that borderline thing.
So we want to identify those zeros and then make those lines. Yep. So here are our zeros to across the x-axis, making those lines down. And then we want to pay attention to each of those intervals in between. What do we want to look for?
Negative minus. I meant plus or minus.
We need those plus or minuses. What do I mean by that?
Two
You want to add
negatives
that?
and a positive.
Oh yeah.
2 negatives and positive. What's negative and what's positive?
The two roots in the back, so you look at
Yeah, like those two lines are negative and that one's positive.
Okay, yeah. So those linear factors we can identify on this left side to the left of that negative 1, x equals negative 1. We can see that 2 of the linear factors are negative, 1 is positive.
So it's a negative.
We multiply them together. What's a negative times a positive?
Negative.
Negative.
Positive.
Negative, positive, which one?
It's positive.
Positive. Negative times a negative is a positive. Positive times a positive. So we know that we are going above the x-axis. Okay. What about in between here?
Negative, negative.
I have a negative, negative, positive. What's a negative times a negative times a positive? Positive again. So notice how we came down to the 0 and then what do we do again? What do we call this motion?
Bounce.
We bounced off, right? So what else is occurring when we bounce off like that? What words were we using to describe it? We have a double root. So notice how 2 of my linear factors shared that 0. So it was a double root, and so we bounced off. So I'm back up, and then I have to come back down to my next 0. And then what are my values like down here, or to the right-hand side?
Negative, positive.
Negative, positive.
Negative,
Okay.
positive.
See this one going up here as well.
Yes.
A positive. So negative times a positive is
Negative.
negative. So now I'm coming back down here. Does that be perfect? But that is that shape that we identify from those linear factors. Okay, so now from here, I want us all to move to part B. Let's see if we can construct this polynomial in standard form. Good idea. Good idea.
There's going to be a Maxwell
I'm going to ask you to keep this for now. So I can later.
What probably could be done is finishing this up and then reviewing the great straight understanding that we will have in the second half of the day. That demonstration understanding will be on.
I'm gonna plan that.
Okay, how are we gonna find the standard
graph of a function using the factor like this, identifying
Oh, camera roll. Turn this on.
area models recognize that we could multiply the first two together, or I noticed that the queens, they multiplied the first and the third one together. That's totally okay. We can choose the order in which we multiply these, as long as we make sure to multiply each one. Now, something I want to caution, as I saw a couple groups, they did great on that first area model. When they moved to the next one, so they noticed that we have those 4 boxes, those 4 areas, and then what they did with this group here is that they kept it as negative 6x and 2x when they moved to that next step. Now, keep in mind that this is mathematically sound. We can do that. We don't have to combine these like terms before we move on, but it will help us stay more consistent. Because what happened here is that it looks like this group, it seems like we missed a little bit. So that 2x squared times negative x, negative 2x squared, negative 6x times negative x, positive 6x squared. That 2x times negative x should be what? What's 2x times negative x?
Mr. Can you look at
2x times.
2x should be a negative 2x squared here. So the thing is that when we have it written like this, also it looks like we should have had a negative x minus 1 here, unless we wrote it as a plus 1. We just want to make sure it's useful for us to go ahead and combine those like terms earlier, so that we can go ahead and, so we don't have to write out as much, we're less likely to make mistakes as we move on to the next piece. But I like what a lot of the groups had when they ended up combining those like terms. We ended up getting, negative 2x squared, negative 2x cubed, plus 2x squared, plus 10x, plus 6. Okay. Does anyone have any questions on finding that standard form? Yes,
I think the bottom one, negative 2x. Why negative 2x squared?
So when we're doing the area model, you want to make sure we're grabbing, so for that box here, that was the product of 2x.
The bottom.
The bottom one?
Negative, yeah, like 2x squared is supposed to be negative.
Yeah. So good point. So when we include that negative 1 in there, this should have been a negative 2x squared.
And it's 6x.
This should be a positive 6x.
Yeah.
Maybe 6 times negative 1. 2x times negative 1 would be a negative 2x.
Yeah.
And then negative 6 times negative 1 would be a positive 6. Yeah.
Yeah.
So that's what we would have done if we split into 4. Or we could have went ahead and combined those like terms. So if we had done that, so if we had done it here, so we did 2x squared, negative 6x plus 2x, is negative 4. Hey, Mr. Robbie, I got it right here. Oh, thank you. We can look over here at the kings. You can see that.
But hey, Mr. Ken, I got one question.
Let Mr. Robbie explain, you can ask questions if you need to.
Here. So we can see here that we can multiply. We've multiplied those first 2 linear factors together. 2x squared minus 4x minus 6. When we make another, we can make another area model. Multiply that with negative x minus 1, and then perform the product into those boxes. From there, can you notice that we can combine these like terms? 4x squared and negative 2x squared, 6x plus 4x, and that's how we were able to get that resulting function. Now, Tosh, what's the question?
So like, how is it gonna be a positive 2x squared? Cause ain't it a negative? So wouldn't that be a subtraction?
Yes, right, this positive 2x squared. So that was obtained from combining these like terms. The negative 4x times negative x is positive 4x squared. 2x squared times negative 1
Wait, so
is negative 2x squared.
it's wait.
Yes.
You put again how you had an fx was negative 2x thirds plus 2x squared and all the plus 10x plus 6.
You're asking where this came from?
All this came from, yeah. From after
So-
we did the box.
So all of that came from combining those like terms inside of that area model.
Can you make
So,
that
so just like up here, so I think Ricardo, I noticed that you guys did this great. You guys were able to grab these 4 pieces, those 4 parts of the area model, and then write it out as is. Now, keep in mind, we couldn't combine those like terms.
I think that's what Vicari's missing. Vicari, remember, 2x squared, are there any other quadratic terms in there? Like if you look at that top, if you look at the top square, are there any like,
Negative 2x squared?
no, the 2x squared at the very top, right there. Are
Right.
there, in that model, are there any other square terms?
No.
So then it's just 2x squared. But when I look at 2x, are there any terms that are like that 2x?
2x squared. The square root.
But you just said the square, that's squared, right?
Negative 6x.
So the negative 6x. So one thing in this, Mr. Harvey, this is something I always try to focus on. Instead of just saying combining like terms, we're adding like terms. We're taking 2x and we're subtracting 6x.
Right, but I'm trying to figure out what a 2x squared plus 10x plus 6 is.
That's what we're trying to explain to you, Vicari. So remember how 2x minus 6x is negative 4x?
Yes.
So now, we see how we circled those like terms. So Mr. Harvey, if you can move down to the next one, or the, so negative 2x squared plus 4x squared. What's negative 2 plus 4? Or 4 minus 2 is 2, so 2x squared. We have positive 2x. I said negative 2 plus 4 or 4 minus 2.
Oh.
Let's see, I'm trying to keep it for a minute.
No.
Okay.
Mr. Harvey is going, how about this? Mr. Harvey's going to get us started on the next piece.
Oh, I see. Like the plus 6x and the plus 4x. You add that, and that's how you got 10x, right?
Yes.
Now for the 6, since that's just plain, you put the 6 right there, right?
Right.
But where did 2x squared came from again? Like the 4x
Vicari,
squared
what's 4 minus 2?
minus 2.
Yeah, 4
I got
minus
you
2
now.
is 2.
Yeah.
Okay.
Yeah.
Mr. Harvey, do you want to start going over, what are we on, C now?
Yeah.
Actually, can we give them just a minute to write down
Yeah.
one of the area models? Please make a note to yourself about how we're using that area model, right? Because that's something that will be on your next demonstrate understanding, is using that area model to multiply 2 or even 3 factors. Did you not get one of these?
No, none of all good.
Oh, we just missed you.
Sorry, I thought Mr. Kenny was.
Well, that's the higher, that's not.
Oh, my bad, wrong one.
Okay.
That's what we're about to use.
I think you have an hour, right?
I did. My bad. Excuse me.
My fault. Mess.
Where are you supposed to be?
In my car key.
I didn't ask.
No, I ain't gonna go back like this.
You tell me and I take your.
That wasn't my fault. That was my fault.
I did not ask. Where's Chris? Oh, you got it. Guys, have y'all taken a single note yet? Written a single thing down to help you improve your understanding. No, you were not. You were not looking for anything. You just sit, bro.
I'm trying to get this stuff off the zero.
Okay. If you're sitting here doing nothing, you ain't actively looking for an answer.
You will hit my elbow.
Hey Tyler, have you written any of this stuff down yet? Yes, dude. Since this is me, since I left over there saying, hey, Mr. Hobby, can we give him a minute or two to write this down? And y'all haven't done anything since.
Can I ask you a question?
No, sorry.
Okay, it's like, what is the noise? He gets sarcastic, okay? What the voice like? Yeah. That's how I figure something out.
I just sit
Hey,
there.
look,
Mr. Hobby, pointing out that instead of doing negative 6x plus 2x, go ahead and make this negative 4x.
Why?
Because
But I had to tell out the.
So that's -4, right? And so 2x minus 6x, 2x minus 6x is -4. So now I simplify it.
So see, you need two.
One thing I got in the bag of hot
Positive
chicken.
2
Well, he said, I just really want it.
is right here. Like use a calculator, you got to put it there. 2 minus 6 is -4.
Negative.
That's right. Negative x minus 1. Negative x times 2x squared. Negative x times 2. Negative x times negative 6. Negative 1 times 2.
Everyone should have.
Negative 2 plus 1. Positive 2. Which is already positive 2x squared. 4 plus 6 is 10.
Did you check all the notes that we wanted to? The first can't see it. Oh, I see it. So, any notes that you want to take in this first couple parts?
All he talking about the bird.
What y'all got?
So you do probably do so right now to do about that.
Not like there was a lot of people at the school, like in the stadium.
Why haven't
When to be. Keep asking.
I said, walk there.
Because I don't
I seen him.
right here.
Football Listen, big hits. You know something? I'm glad you had fun.
I'm sorry, but who is he talking to?
Thank you. Thank you, Addison. Thank you, Bakari. Thank you, Mel. So, Mr. Hobby is about to continue, and some of us are going to get miffed that Mr. Hobby is already starting, but it's been 4 to 5 minutes since I and Mr. Hobby explicitly asked you to write down this and whatever notes you need to about going from factor form to standard form. Like, if you're doing nothing, you're getting nothing out. If we asked you to do something, I would expect within the first 30 seconds that we already have our pencil out ready to go and writing this stuff down. Sometimes it's not that we can't understand, sometimes it's just that we're not doing the things to be successful. This whole time, I've been walking around to see if I could answer any questions, but almost half of us hadn't even started something until I got to your group. If you need a pencil, ask for one. Don't just sit there and do nothing. You do nothing, you get nothing out of it. And if you have a friend next to you who's doing nothing, in a respectful way, not disrespectful way, respectful way, suggest that they do something. If someone's talking to you, not about the math, and you know you need to learn something, respectfully say, hey, I'm trying to learn something. Because you are responsible for what you have learned at the end of the day. So, let's stop making excuses. Let's stop getting pissed off when I try to redirect you to do the things you need to do if you're that person. And let's do some learning. Mr. Hobby.
Alright. Okay. So, we talked about parts A and B. We're going to walk together through the rest of this page so that we can go ahead and jump straight to the activity from there. So, talking about part C. What is the degree of your polynomial? 3. How do we know that the degree is 3?
Well, it's about 3 roots out of x.
That's the highest power.
3.
That's how you
It's
find
The highest power
Three
is 3 roots. Okay, I like this. So we're talking about the power, we're talking about the roots. What is it that, so we want to make sure that we're looking at standard form here, right, and capturing that highest power. Nice. So we saw that our highest power was 3. And also, Bakari mentioned that we also know that we have 3 roots. What do we call that again? How do we know those 3 roots?
zeros.
So they're also known as zeros,
The
but
function as well, right?
Factors.
specifically
Given
there's
function?
a property that tells us, that connects the
I wouldn't know.
degree to the roots.
The algebra.
You talking about
The fundamental theorem.
fundamental theorem of algebra?
Fundamental theorem of algebra, yeah, so we know n equals 3 because we can see that the highest power, also known as the degree, is 3. And also, because of the fundamental theorem of algebra, we know that we're going to have 3 roots. So it looks like we actually went ahead and answered a little bit of D. So part D here, how many x-intercepts are there, and how many roots are there? How many zeros? 3?
Wait, is that a D or is that like an H? Top right there.
Top here, this is an N.
Why you got H there?
So N, so good question actually. So
I get a
N,
piece of candy fast, that's a good question, right?
what?
I get a piece of candy fast, that's a good question.
Sure.
Stop being a fan.
Sure, you gotta
So,
get it.
Right now, I guess.
So N is the variable, it's the letter that we're going to use to represent that degree of that
You
polynomial.
do like us.
You see N,
Let's do it.
that's a perfect degree. Now, it's going to be a little different from multiplicity. Now,
I do want to pause and point this out. Moving forward, if you ask for a piece of candy, you ain't getting a piece of candy. You get a piece of candy because we thought that was a really good question to push people's understanding forward. We're not rewarding it if you're asking for it.
He said that was a good question, Miss Candy.
For asking what his handwriting
But-
is, it's not a good question.
But, no, back up. If you at any point ask for a piece of candy, you ain't getting a piece of candy. Okay.
okay. So I absolutely agree with you guys. There are 3 roots. There are 3 zeros. What are the zeros? What are the roots?
What are the
3 and -1.
The roots
We did erase them. Can we determine them graphically?
What's 3 and -1?
What was that?
3 and -1.
3 and negative 1. So how did you know that it was 3 and negative 1?
What I did.
It said the factor equals 0.
So so that's what we can do algebraically, and I saw that you guys were doing that earlier in the class. We can take our factors, set them equal to 0, and solve for them. Now, how can I determine my zeros graphically?
3.
Where do zeros occur in my graph?
x-axis.
The x-axis. They're on the x-axis, so they're zeros. That's where they intersect. So we can see here we actually have -1 and 3 here. I know it's a little weird actually how it came out. That should be 3. So here we see that x equals -1 and x equals 3, but that's only 2, right?
It's a double root for -1.
There's a double root. Okay. How did you know there was a double root?
Because there's 2 more.
So 2 of our, what 2 things ended up intercepting there? It was those 2 lines, those 2 linear factors. When we had those 2 intercepts, what did the graph do at that double root?
It
Bounce,
bounced.
yeah. So if we recognize that our function is bouncing off of that x-axis, that also tells us that we have a double root there. So what do we call the number of times, what do we call the number of roots that we have? What word do we use?
You talking about the turns?
Well, we're gonna, not quite the turns, that's referring to something else.
You said the number of roots we use?
But there was a certain M word that we use to describe how many times.
Multiplicity.
Multiplicity, yeah. So if it's a double root of -1, what's the multiplicity? 2. So we x equals -1, the multiplicity of 2. X equals 3 with a multiplicity of 1. How'd you know it would be 1?
Because it's a multiplicity of 1.
It goes all the way through.
Because
He said it goes all the way through.
it went through? Do we agree with that?
That's what I said. I said it.
Yeah, so because we crossed the x-axis at x equals 3, that meant that multiplicity ended up being 1 when we crossed that x-axis.
Oh, wow.
Now, keep in mind, so these are zeros. What are our x-intercepts?
Our x-intercepts
Yeah.
are those.
What are they?
-1, -1, then 3,
-1, 0, -3, 0. How'd you know that's 1?
He did it copy on me.
X equals,
Come on,
Sorry.
bro.
Jamie, how'd you
Come on,
know?
bro.
Because that's where.
X equals 0? Oh, my bad. I thought
Say it again.
That's where cross the x-axis at.
That's- Yeah, so that's where the function crosses the x-axis. We cross at -1, 0. We cross at 3, 0. Now, I want you guys to pay close attention to the notation here. I wrote these a little bit differently, right?
Yeah.
How did I write these roots and zeros? What did I do?
As equal.
I wrote it as an x equals, right? That value of x is a 0. How did I write these x-intercepts?
Yeah.
These are coordinates. These are points on the graph. Also, keep in mind that I have 3 roots. How many x-intercepts do I have?
You have, you got 2 in the first. Yeah, 2.
I only have 2 x-intercepts. Yeah. So that's something that you want to be careful about here. Now, keep in mind, feel free to take this time, write any notes that you want on this. But yes, 3 roots and zeros, but only 2 x-intercepts.
Wait,
Yes, what's up?
are we supposed to be writing this on our polynomial paper or like?
Yeah. So all the things that I've been writing has been on this bell ringer that we passed out at the beginning.
Oh, okay.
So that's parts A through D. So I'm going to give you guys 2 minutes. Write down any notes you want so far on parts C and D.
You got 2
B,
minutes
C, and
right
D.
now, whatever. Read.
I did.
Read out. I can't. It's a read right now. I'm not here with you. I can't read. My word will be split like my word will be split like that. They read. Why you being weird?
I guess so.
What click is it? You can read. Which one you said?
Not really.
You read.
But listen.
2 x-intercepts and 3 zeros. So you have 3. 2 x-intercepts, 3 zeros.
Did you say yes or no?
What you mean? Yes, or no? You didn't give me.
Yeah, 'cause you know. You know not to. You know how I
Yeah, I'm not seeing a ton of pencil to paper, so I'm going to take that to mean that we're done taking notes on these sections, and we're going to move on to part E. Okay, so what is part E asking us here?
How
How many times does the graph turn?
How many times does the graph turn?
So loud.
Do you think it's turning twice?
Dilating, basically. How many times is it dilating?
It's not quite how many times it's dilating, but Taj, why do you think it's turning twice?
Because it bounces off the first one, then it goes back up to come back down, right?
Okay, so you're saying it comes down, comes up at that double
The
root,
curves,
right?
the little curves.
So that's one.
Yeah, the little curves.
Time, where does the other turn occur?
But it goes up, then it goes back
It
down.
goes up and then goes back down, yeah, so that's how many times the graph is turning.
Jump about.
The mins and the maxes, basically.
So, yeah, so notice how, in parentheses here, what does it say right after how many times does the graph turn?
Relative extrema.
Relative extrema, what does it mean by that? Relative
Like,
extrema.
your highest points and your lowest points. Like your relative mins and relative maxes.
Okay, yeah, so we're talking about those relative minimums, relative maximum. So I want you guys to notice here that when we turn, when we do our first turn, what do we have occurring at that first turn? Is it a relative?
Relative min.
Minimum.
Yeah, we have a relative minimum, right? We can see that when we zoom in on that point, we can see that we're going from a decreasing piece to increasing. So we're going negative. Now, what about the second turn? What is occurring?
Starts to decrease after that.
Starts to decrease, yeah. So we started with increasing originally, and then we came back down to decreasing. What do we call that? Going from increasing to decreasing? Is it?
A bit. Wait, you said what?
When we're going from increasing to decreasing, is that maximum or minimum? What I'm
Minimum.
describing?
Oh, that's a minimum.
From increasing to
Oh,
decreasing.
no, that's
Maximum.
It's a maximum. It's a maximum that's occurring there. So
Wow.
yeah, so we can notice that those, when we talk about those two terms, that's talking about that extrema. Do you want to talk about that specifically, what that extrema? Okay.
for this time, so you can
Yeah.
at least get into a task.
Yeah, so we're gonna say for now that, yeah, there are 2 terms. And if you want, if you have the function graph, then you can circle those,
Wait, what?
refer to them however you want. We saw there were 2 terms, right? There was a maximum, there was a minimum first, at that first turn, and then a maximum at that next turn.
Yeah, I was talking about what you had wrote.
Oh, yeah, 2 turns. 2 turns.
No, yeah, put T-U-N-S.
Okay. So, let's look at the next piece, part F. What is part F asking for?
The leading term of the polynomial.
The
And
leading term,
coefficient.
leading term and the leading coefficient.
Yes.
Okay, does anyone have an idea what the leading term might be? What the leading coefficient might be?
Leading coefficient of first number, like the number in front.
Leading coefficient is the first number in front. So that means that for this function, what would it be?
2, negative 2.
Would it be that -2?
Yeah.
Okay, gotcha. So let me give you another example. If I wrote f of x equals 2x squared plus 5x cubed plus 3.
Yeah, 2.
Leading coefficient would be 2.
Wait, or would it be the one with the highest power? I mean power.
One with the highest power.
Would it be your number with the highest degree, or just the number in front? Oh, right. I forgot.
So Dewan is asking right now, that leading coefficient, is that just what's at the very front of the function? Or is it the coefficient that is attached to my highest power? What do we think?
The highest power.
It's going to be the highest power, yeah. So when we're in standard form, when we write, so what I wrote here wasn't neat standard form, it wasn't good standard form. Whenever we write standard form, we always want to write that highest degree, that highest power first. So I really should have written it like this.
Yeah.
And yeah, so that leading coefficient, what I mean by that, so the leading coefficient refers to the coefficient, whatever that constant value that's being multiplied by that highest degree term.
Let's write that on F, right?
Yeah, write that in F. I'm only writing it down.
What does the L and C mean again?
So L and C stands for leading
Leading
coefficient.
coefficient?
Leading coefficient.
Leading coefficient.
Leading coefficient?
Yeah, it's written on your sheet.
Yes. Leading
It's
coefficient.
in bold, leading coefficient.
I appreciate that.
Yeah. So if that's the leading coefficient, what do we think the leading term is?
The what you call it?
What is a term in math? What am I referring to? A number? A letter?
Oh, like a problem. Like
Problem?
An equation, right?
No, we're not doing that.
It's gonna be X. X.
So if I pointed at this and I told you to give me a term. 6 would be a term. What else is a term?
Like terms? Like terms?
Well, it's kind of like terms, yeah. Now, keep in mind when we're talking about like terms, we're referring to, like Mr. Kenny said, adding them together, combining those like terms.
Ooh, listen.
She's on her way.
That's a good point.
Are you the office announcer or?
So guys, remember over here, when we were combining those like terms, we had a -6x and we had a 2x, right? These are both terms. Those are terms that we can then able to combine. That's why we call it like terms, is because these are individual terms that are like because they're both variables. They both have their variable raised to the 1.
Yeah.
So, I like what, so Winter, you remember I checked it when you said like a number? Yes, a number is a part of it, but it's not just a number by itself. It's a number and whatever, the number is the coefficient to whatever variable we're referring to. So those are what terms are. So which of our terms is our leading term?
Well, probably was the number in the first, the negative
2 at third.
on that.
The -2?
Third. Yeah, 2 at the third.
So is it -2? Is it x to the third? Is it
I mean
-2x to the third?
-2 x to the third.
-2x to the third, yeah. So this entire piece that entire term is our leading term. So yeah. So notice how, so let me go back to this one. This example here. What is my leading term? 2x squared plus 5x cubed plus 3, what is my leading term?
5 is 2.
It's going to be that 5x cubed again, yeah. So not necessarily the one that's in front. If they were in standard form, then yes, it would be in front. But when we have it written out like this, we want to make sure that that leading term is whatever has that highest power variable. Yeah, so leading term refers to the whole term with the highest degree. Okay. Do you have any questions? Comments, concerns?
Oh yeah, my question is
What's up?
for which bullet? Which one was it? Forgot what question it was. But are we running based on that? The white one?
Yeah, so this, yeah, so this is the function that we're working on. So this is, so that function that we started with at the very top,
Yeah.
we found that the standard form was this one down here. Yes.
Okay, my fault.
No, you're good. Yes. You guys were confused. This is that standard form that I'm referring to when we're talking about that leading term. So that means that the leading coefficient was -2,
Right, 2 is to the third.
and that leading term was -2x raised to the 3. Okay. Give you guys 60 seconds. Write initial notes you have.
So in essence, I got term was highest degree.
Mike, why do you have a dash in front of your teeth? It's not a negative side. That. Why so low? Okay. Oh, you have a dash. Put it in front of the tooth. There you go.
I can't see Miss Holly.
Okay, let's move on now. So going once, going twice. Any questions?
That was good.
You got one
All
more?
right.
Please don't.
I don't have a question.
What's your question, Craig?
I said I have a
Oh,
question.
you don't have it. Okay, got it. Okay. Part G. So notice, well, now we're going to move into something a little bit new. Maybe something you guys have seen before. Talking about end behavior.
Yeah.
Talking about that behavior of the end. So, part G. As your graph goes farther and farther to the left, what direction does the graph go vertically? As your graph goes farther and farther to the right, what direction does the graph go vertically? So, looking at our graph up here, looks like we got a piece of it erased actually. So I'm going to really quickly rewrite it. This is our graph here. Okay. So, looking at the shape of that graph, as I travel further and further to the left, what is happening to the graph vertically? Is it going up? Going down?
Going up.
Yeah, it's going up. So that is how we can describe it, like without all that mathematical language. But really, when I talk about traveling further and further to the left, what is x doing as I go further and further to the left?
Ain't going negative.
It's getting negativer and negativer, right? Yeah, so it's just becoming more and more negative, right? And what is it, like if I just keep going this way,
It's
it's going, right? Yeah, it's going towards negative infinity. So basically we can say that when it travels this way to the left, we can say that x is approaching that negative infinity. As x approaches negative infinity, what's y doing? What's happening vertically?
Going.
It's going up.
Going. Yeah.
right? So we can see that we're traveling upward, up into the sky, into the stratosphere. We can see that we're traveling upward. Now, we're going to use some very specific notation to describe it. So when we're talking about that leftward movement, we're going to say x is approaching negative infinity. Now, when I talk about approaching, I'm going to use this arrow symbol. That arrow is what we use in mathematics to refer to that approach.
Minimum.
It's heading towards it.
Minimum x.
Not necessarily a
You got a
minimum.
negative, don't it? That's a negative.
This is a negative infinity because it's traveling to the
So
left.
it's minimum x.
Well, infinity isn't really a minimum, but it is decreasing towards negative infinity. And we're going to say that as x is approaching negative infinity, what's y approaching? Y is approaching positive infinity. So that's how we describe the behavior on the left-hand side of the graph. Now, LHS is what you'll see. Yeah, it's still going here.
Mr. Hobby is up here trying to teach, and most of us are packing when we still got some major information that you need to learn. Some of us sitting there with a backpack on, not even like a shred of paper out. Some of us having side conversations. Mr. Hobby, can you please continue? Because I'm going to be using this information tomorrow. Like, the plan was, and Mr. Hobby slowed down to help you guys out who played around a whole lot earlier, was to be done with this before lunch and do the thing I'm going to do tomorrow after lunch. This is the problem, is that we play around a little too much instead of trying to learn something. Mr. Hobby, can you please finish explaining this in the next minute so that we can pack up with 1 minute to go?
Absolutely. So as I described at the left-hand side, this left-hand end of the graph of the function, we just say that as x is approaching negative infinity, as it's going to the left, y is increasing, heading toward up and up towards infinity. Now that's on the left-hand side. We want to talk about the other side as well. On the right-hand side, what is x approaching as we travel further and further to the right?
Negative. Oh, you said x?
As we go to the right, that's
Positive infinity.
approaching positive infinity.
Yeah.
That's how we describe this then. And then vertically, what is happening, what is y doing as we travel this way?
Negative.
It's going down. It's becoming more negative, right, as we said. So what would we say y is approaching here?
I mean positive infinity. I mean negative infinity.
So y is decreasing, going down, 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 into the floor, into the first floor, into the ground. It is approaching negative infinity. So that's important when discussing that behavior of the ends. We want to discuss what is the graph trending towards, what direction generally is it going on those ends. That's why we call it the end behavior.
Last detail before we go, I just want to point out those arrows that Mr. Hobby drew, that literally means the word approach. Doesn't mean x equals, it means x approaches those infinities. I have not decided yet, based on what I'm seeing, if we're going to do the demonstrated understanding tomorrow at the end of class or on Wednesday, but it will be one of those 2 times. I will be passing back the study guides tomorrow, and some of us still need to work on that math stuff.
Go.
That's probably what happened. Kenny, make sure you watch that video back. You see all